So in section 2, we're going to be working on solving different types of equations. So this is going to go through several different types of equations we've learned about through the process of Algebra 1 and Algebra 2. So we're going to work on solving linear equations in one variable and also solving rational equations. We're going to work with quadratic equations, and we've learned 4 basic methods for doing that: factoring, finding square roots, completing the square, and using the quadratic formula. We're going to solve polynomial equations that are cubic or higher, or a degree of 3 or greater. We're going to solve radical equations, and we're going to solve absolute value equations. So when you think about equations, an equation is a statement that 2 algebraic expressions are equal. And here are some examples of what equations look like. You're familiar with that. And of course, the difference between an expression and an equation is, equations have an equal sign, whereas expressions don't. Okay, and what we do when we solve equations is we do a series of steps until we find what x is equal to. And in each case of those steps, we're transforming our equation into an equivalent equation by doing things that we're allowed to do by adding to either side, by subtracting from either side, and things like that. And there are a lot of different types of solutions, some sort of, or different types of equations. So we have identity equations, and identity equations are always true. They're true for any value of x. That's important, right? It's a true statement for any value of x. And we have conditional equations, which are true sometimes, so for specific values of x. And we have contradictions, that are false for every real number. And typically what we work with for an equation that's true for just some, remember that was conditional. What we tend to work with is conditional equations, but often we're in identity or other types. And when we talk about looking at equations, what are equations? A linear equation in one variable has the variable x no higher than the first degree. That's what a linear equation is. And as I mentioned before, as we solve, we create equivalent equations by making changes. So for instance, 2x minus x would be my supplied, the left side of this equation. And when I actually perform that subtraction, I get an equivalent equation of x is equal to 4. So these are things you've done quite a bit. But we don't always talk about the concept that we're taking an equation and making iterative equivalent equations until we get to our solution, x equals the rest of our equation. So what does that look like? If I want to solve these equations, we do things like I'm going to add 2x to either side. And then I would subtract 15. So I've made one equivalent equation, a second equivalent equation. I'm going to divide by 2. And now I've reached the end and I've solved for x. So when I say iterative, it means each time we make something new. So we're continuing to work with this process of making an equivalent equation, then another equivalent equation, and then another equivalent equation that eventually satisfies what our goal is. And the same way here, if I subtract 5x from either side and add 9, and then divide by 2. Okay, so those were linear equations, and that was the process by which we sort of go about solving them. Very familiar for you from pre-algebra and algebra 1. Now, rational equations are equations that involve one or more fractional expressions. So you see over here, I have 1, 2, 3 fractions in this particular equation. And there are a number of different ways you can go about solving these. I can get rid of all the fractions. I can always get rid of all the fractions by multiplying both sides of the equation by the least common denominator. Okay, and in this case, the least common denominator is 9. So if I multiply everything in here by 9, when I multiply 4x divided by 9, I just get 4x. When I multiply 1/3 by 9, I'm going to get 3. When I multiply x by 9, I'll get 9x. And when I multiply 9 by 5/3 or 5/3 by 9, I'm going to get 15. Okay, the nice part about multiplying by the least common denominator is that all the fractions go away. And that leaves us with something simpler to deal with. So I'm going to subtract 4x, and I'm going to subtract 15, and then I'm going to divide by 5. Okay, and in this particular case, I ended up with a solution that was a fraction as well. Now, is this the only way to go about it? No. No, I could actually do the addition and subtraction on either side. So I could go ahead and create common denominators like that, and I could have 3x over 3 plus 5 over 3. And then what I'll end up with is 4x minus 3 over 9 being equal to 3x plus 5 divided by 3. And then I would cross multiply. 9 times 3x plus 5 is equal to 3 times 4x minus 3. And if I divide both sides by 3, I'll get this, and I'll get 9x plus 15 is equal to 4x minus 3. But look at this. You'll notice that this moment right here is that moment right there. So a few extra steps for sure, but in the end I'm going to the same place, and that's the place. X is equal to negative 18/5. Okay, sometimes when we do this kind of work we end up with extraneous solutions. And an extraneous solution is a solution that doesn't satisfy the original equation. So we solve for it, but when we actually plug it back into our equation, it should create a true statement, and instead it creates a false statement. That would be an extraneous solution. If I work on solving this equation, I notice as I'm looking at the problem that these fractions have common denominators. Well, that's great. Why don't I just subtract 12 over x minus 4 from both sides? Equally, I could multiply both sides of the equation by the common denominator. And I'll probably show you what that looks like here in a second. So I'll have 3x minus 12 over x minus 4 is equal to 5. And then I'll multiply both sides of the equation by x minus 4, which is going to give me 5x minus 20 is equal to 3x minus 12. If I subtract 3x, I'll get 2x. If I add 20, I'll get 8. And I'll go x divided by 2, x is equal to 4. But wait, if I plug 4 back into this original equation, my denominators will both equal 0. I can't have that. This is an extraneous solution, so this ends up having no solution. Okay, so I'm not going to bother going back and doing it by multiplying by the least common denominator. It works out largely the same. But there's no point because I have no solutions. When we start working on with quadratic equations, we learned a number of different ways to solve them. We learned that we could solve by taking square roots. So if I can get my variable in something that is squared and everything else on the other side of the equation, then I could take the square root of either side, which is the way this works, and I can find a solution. We learned how to factor, and in this case I'm factoring with a leading coefficient of 1. So I would want to find factors of 6 that have a difference of 1, or in this case negative 1, so that would be negative 3 and 2. And then I can find solutions. When my equations weren't factorable, we learned how to complete the square. And you'll notice if you look at completing the square, what I'm left with once I've completed the square is the first case we talked about. Something squared that contains my variable equals everything else. That's what that looks like right here in this step here. Something squared that contains my variable is equal to everything else. I take the square root of either side. And then we also learned about the quadratic formula. Okay, so in this case I put my equation into standard form. I identify A, B, and C. And in this case A, B, and C are these guys here. And I plug them into the formula and I work out a solution. Okay, so 4 basic methods for the quadratic functions. Let's take a look at what that looks like. If I want to solve by factoring, the first thing I need to do is put it into standard form. So by subtracting 6 from either side, I put it in standard form and I make it equal 0, which is what we want. Then I want the factors of 2 times the factors of 5 coming out with a difference of 3. Well, the factors of 2 are 2 and 1, the factors of 5 are 5 and 1. 2 times 1 is 2, 1 times 5 is 5, and they have a difference of 3. So I know that I'm going to go ahead and put 2x in one of these binomials, and I'm going to put x in the other. I need a plus and a minus. Now I've got to come out with negative 5x, because what we need for our middle terms are negative 5x and positive 2x. That's what's going to give me negative 3. So I'm going to negative 5 plus 1. So you'll see in terms of insides and outsides, my first make 2x squared, that's great. My last make negative 5, that's good. My insides and outsides make negative 5x and plus 2x, and I know that that's going to combine to make negative 3. So that's sort of the process of factoring. If we want to solve by using square roots, if I work on these problems, if I have 3x squared is equal to 36, I want to divide both sides by 3. So x squared would be equal to 12. And then if I take square roots, I also introduce plus and minus. So I'd have the square root of 12, which should be simplified to be 2 root 3. And I did that because the square root of 12 is equal to the square root of 4 times the square root of 3, and the square root of 4 is 2. That's how I went ahead and simplified there. And if we look at the B problem, this was A, the B problem, I have x minus 1 squared is equal to 10. If I square root either side, I'll get x minus 1 is equal to plus or minus the square root of 10. And the last thing I'd want to do would be to add 1 to either side, so I'll have 1 plus or minus root 10. Okay, so that's finding solutions to quadratics by taking square roots. I might want to complete the square. Now, completing the square requires your leading coefficient to be 1. So if it already is 1, that's great. You can just move on and do the work. And completing the square is about creating the perfect square of a binomial. And the first thing I'd need to do in this problem is get rid of that constant, negative 1, because it doesn't help my solving the problem. So if I add it to either side of the equation, and then I'm going to take this coefficient here. From standard form, it's the b coefficient. I'm going to divide it by 2, and I'm going to square it. So 4 divided by 2 is 2, and 2 squared would be 4. So I'm going to have x squared minus 4x plus 2 squared. And there's a reason I'm writing it as 2 squared on this side. And over here I have 1 plus 4. And I write it as 2 squared because we're now moving into this binomial x minus 2 squared. And I did that so I don't forget the fact that I'm looking for the 2. I'm not really looking for the 4. Right? It's important. When I make this binomial, I'm using this, this, and this to create the binomial. Okay, the next thing I would want to do, now I'm in the first case, like I talked about before. I'm now in the first case where I have something squared that contains my variable equals everything else, and I'm going to solve by taking square roots. So x minus 2 would be equal to plus or minus the square root of 5. So x will be equal to 2 plus or minus root 5. Okay, if my leading coefficient isn't 1, I have to make it 1 before I start doing the work. So in this case, I'm already in standard form. I'm going to divide everything by 3. So I have 3x squared minus 10x minus 2, and I'm going to divide the whole thing by 3, equals 0 divided by 3, which is still 0. So this becomes x squared minus 10 thirds x minus 2 thirds. Now I want to complete the square, so I'm going to get rid of the constant by adding it to both sides of the equation. Sorry, not 2/5, 2 thirds. And I'll have x squared minus 10 thirds x. So I'm going to take 10 thirds x, I'm going to divide it by 2, which makes 10 sixths x, and I'm going to square it. That's 136ths. Okay, so I'm going to have x squared minus 10 thirds x plus 10 sixths squared. And on the other side, I have 2 thirds plus 136ths. Okay, and I did this because this is x minus 10 sixths squared. And on this side, I'll need to make common denominators, so 2 thirds would be 24 36ths plus 136ths. And I'm going to take the square root of either side, so I'll have x minus 10 over 6 is equal to plus or minus the square root of 124 over 36. Okay, so 124, I can factor a 4 out of that. So this will be plus or minus, so that's going to be 4 times 31. So I'll have the square root of 4 times the square root of 31 all over the square root of 36, which is 6. And if I add 10 sixths to either side, I'll have 10 sixths plus or minus 2 root 31 over 6, which could be simplified to just be root 31 over 3. Okay, a little complicated. And this actually can be simplified to be 5 thirds as well. 5 thirds plus or minus root 31 over 3. Okay, quite a few steps in that particular case. If we want to use the quadratic formula, I might find 2 solutions, I might find 1, I might find only imaginary solutions. But in this case, I have to first identify a, b, and c. A is equal to 3, b is equal to 2, c is equal to negative 10. I know that x will be equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. And here's my a, my b, and my c. I just need to plug them in here. So I'll have the opposite of 2 plus or minus the square root of 2 squared, which is 4, minus 4 times a, which is 3, times c, which is negative 10, all over 2 times a, which was 3. So this will be negative 2 plus or minus 4 minus, let's see, that's 12. 4 minus negative 120, so that becomes the square root of 124 all over 6. Okay, at this point I would probably want to go ahead and distribute my division. I'll have negative 2 over 6 plus or minus. I want to simplify this, which we did in the last in the last problem, I've got square root of 124 again. So this is 4 times 31. Square root of 4 is 2. Root 31 all over 6. So x will be equal to 1/3 plus or minus root 31 over 3 when I simplify my fractions. Okay, what does it look like if I have only one solution? I would take a look at this problem. Now, what's complicated about this one is we could simplify this. You notice that I know that I could say that A is 18, B is negative 48, and C is 32. But before I start, it really is in my best interest to simplify this as much as I can. And what I can do is I know I can pull a 2 out of everything, so I'll get 9x squared minus 24x plus 16 is equal to 0. So that made my numbers a little bit smaller. And that's it. I can't really simplify it any further. So now I'm going to find the opposite of b. So the opposite of negative 24 is 24. Plus or minus the square root of 24 squared minus 4 times 9 times 16. And that's going to be over 2 times a, which is 9. And what happens when I pull out a calculator here is I'm going to find 24 squared. 24 squared is 576. 576. And if I go back to my calculator and I have 4 times 9 times 16, 4 times 9 times 16 is also equal to 576. And this is why I have only one solution, is I'm going to have 24 plus and minus 0. Well, 24 plus 0 is 24, and 24 minus 0 is 24. So I just ended up with 24/18, which can be, by factoring a 6 out of each of these things, that can end up as 4/3. Right, and that's my solution. Okay, when we look at higher polynomials, a polynomial will have typically as many solutions as the degree. In that last example, we had a degree of 2, but we only found one solution, and that's because our two solutions were both the same value. We had 24 plus 0, which over 18, which simplifies to be 4/3, and we had 24 minus 0 over 18, which also simplifies to be 4/3. So we actually had one repeated solution, counts as two solutions. In this case, it's a 4th degree function, so I'm expecting to find 4 solutions. And I would want to start by factoring what I can out of these terms. So I can factor out a 3 and an x squared. So when I factor the 3 out of the 9, I'll get 9. And when I factor the x squared out of x to the 4th, I'll get x squared. And over here, when I factor the 3 out of the 12, I'll get a 4, and the x squared would just be 1. And then I look at this guy here and I go, well, 9x squared, that's the value 3x squared. And 4 is 2 squared. So what I've got is the difference of 2 squares. And I know that those will factor to be 3x plus 2 times 3x minus 2. And now if I want to solve, for each x I'll have a solution that makes the equation equal 0. Well, for this one they're both 0. For this one it would be negative 2/3. And for this one it would be positive 2/3. And there are my 4 solutions. Now one of them is repeated, so it really looks like there are only 3, but in reality there were 4. Okay, a couple more examples of a slightly different case. This one really was in a quadratic form, meaning mostly I use skills from quadratic equations to factor that out. These are a little different. If I work on the A problem here, I'm going to try factoring by grouping with this. When I first look at it, I'm looking, is there something I can factor out of all the terms? No, nothing common to all four terms. Then the next thing I would look at would be special patterns. Well, the first term is a perfect cube, but the last term is not. So I know it won't fit any special patterns. So the next thing I do is I would go to grouping. What I'm going to do is I'm going to divide the left-hand side of this equation into two separate groups. Now, when I put parentheses on after a minus sign, when I create the group after the minus sign, I've got to switch the sign. So minus 2x becomes 2x, and plus 10 becomes minus 10. So the same thing we would have done taking parentheses off, we have to do when we put parentheses on around distributing the -1 here, right? There's essentially a -1 right there. And I do this so that I can look at my two different parts of my equation separately. Well, because I can factor something out of these, I can factor x squared out. And that's going to be x squared times x minus 5. And over here I could factor a 2 out. And that's going to be 2 times x minus 5. And when this binomial and this binomial are the same, I can successfully move on and factor by grouping. And I'm going to make a new binomial out of this, this, and this. So then I'll get x squared minus 2 times x minus 5 is equal to 0. And now I would go about solving my equation. So this solution will give me 5. And when I set this to be equal to 0, if I set x squared minus 2 to be equal to 0, I'll get x squared equals 2. So in this case, x will be equal to plus or minus the square root of 2. So plus and minus the square root of 2 and 5, 3 solutions for a third degree function. When you look at the B equation, it's a little different. So I have 6x cubed minus 27x squared minus 54x is equal to 0. I can factor an x out of all of this, and I could also factor a 3 out of all of this. So I'll have 2x squared, and I'll have 9x, and I'll have minus 20. Now when I factor a 3 out of 54, I get 18. Equals 0. Now I want to work on this one. So now you'll notice that I'm not working with a cubic function anymore. I already know the solution is going to come from this. It's going to be 0. But with this one, I want to work at, can I solve it another way? And in this case, I'd probably try to factor. Could I find factors of the products of 2 and 18 that will have a difference of 9? Well, I see that 18 is 3 times 6, and this is 2 times 1. Well, 2 times 6 will give me 12, and 1 times 3 is 3. Those have a difference of 12. So I know that I'll have 2x in one binomial, and I'll have the 6 in the other binomial, so they get multiplied together. They become my lasts. They make the bigger value, so they're going to have that sign that will go with the 6. That means the plus goes here, and an x goes there. And this will give me a solution of -3/2, and this will give me a solution of 6. And these are the 3 solutions I have for this problem. Okay, when we solve radical equations, what we're going to want to do is we're going to want to find a way to get rid of the radical. So normally what that means is I want to isolate the radical. And in this case, that means I would subtract 2 from either side. So I'll have, this is going to be interesting. I have the opposite of the square root of 40 minus 9x would be equal to x minus 2. Okay, and when I square this, remember this is basically negative 1, right? So I have negative 1 times, we'll go ahead and put the negative 1 there, and when I square it, I'm going to square that, and then I'm also going to square the other thing. And I'm going to square this over here, x minus 2 squared. So negative 1 squared just becomes 1. This just becomes 40. Sorry, shouldn't write the square root again. When I square a square root, it becomes just the radicand, 40 minus 9x. And over here it'll be x squared minus 4x plus 4. Now it's a quadratic function. I need to make it equal 0, so I'm going to add 9x. Minus 4x plus 9x is going to be plus 5x. I'm going to subtract 40 minus 36. Now everything equals 0. I would want factors of 36 that have a difference of 5. That would be 4 and 9. So I'll have x plus 9 times x minus 4. So my solutions would be negative 9 and 4. Okay, now I'd want to test those back in here just to make sure I didn't get any extraneous solutions. I'm not going to take the time to do that, but when you're doing your work, you should double check to see. Okay, we have other types of equations, equations with rational exponents. This is a rational exponent. You notice my exponent here is a fraction. How do I get rid of a fractional exponent? Well, I'll take this whole thing to another power that is the inverse of that power. Right? So I'll take this to the 3/2 power, and if I do that on the left side of my equation, I have to do it on the right side of my equation. All right, I do this because when I take a power to a power, I multiply the exponents. This becomes 1. So I'll have x minus 5 to the first power, which is just x minus 5. And over here, I remember that the denominator is a root and the numerator is a fraction. So I want the square root of 16, which is 4, cubed. I'm sorry, I think I said that wrong. The denominator is a root and the numerator is a power. So I'll have 4 to the third power, which would be 64. And then if I want to solve, I'll add 5 to either side. X would be equal to 69. Okay, the key element here is I'm guided by whatever is the original fractional exponent, and I take both sides to its inverse power in order to eliminate it. If I want to work on an absolute value equation, they're a little wacky because what I know is that this item in here can equal 5x plus 12. And I also know that the opposite of it could equal 5x plus 12. Because the absolute value sort of creates opposites. If we go ahead and work on this problem, this one is a quadratic. If I subtract 5x, I'll have 4x minus 5x is minus x, and I'll subtract 12. And in this case, I want to find factors of 12 that have a difference of 1. Those would be 4 and 3. So in this case, x would be equal to 4 or negative 3. When I solve over here, I'm going to move everything to the other side. I always want my leading coefficient to be positive, so I'll add 4x. That becomes 9x plus 12. And here I'd want factors of 12 that add up to be 9. Well, 2 and 6 add up to be 8. 3 and 4 add up to be 7. 1 and 12 add up to be 13. So I don't think that really works out in terms of factoring it, which means over here I would probably go to the quadratic formula. So I'd have the opposite of 9 plus or minus the square root of 9 squared, which is 81, minus 4 times a times c, all over 2 times a. Negative 9 plus or minus 81 minus 48. Well, 81 minus 48 is equal to 33. All over 2. So when I go through and simplify this, I'll have negative 9 halves plus or minus root 33. That can't be simplified anymore, all over 2. Okay, so I have 1, 2, 3, 4 solutions from my absolute value equation. Okay, the key element is I have to solve the equation where what is inside the absolute value is equal to the other side of the equation, and also that its opposite is equal to the other side of the equation. Okay, so just to summarize what we talked about in this particular section, we were talking about identity equations, conditional equations, and contradictions. We talked about what's a linear equation, how do we solve them. We went through 4 methods of solving quadratic equations, and we worked on higher degree polynomials, radical equations, absolute value equations, and we also worked on rational equations. So those are all things you should be pretty comfortable doing at this point.